Hello, my name is Dr. Marlon Lutz at Biosynthetic Technologies. Thank you for joining today's STLE virtual presentation, where I like to take the time to talk about some of the research we've done at Biosynthetic Technologies. The title of my presentation is New Long-Term Hydrolytic Stability Testing on Bio-Based Lubricants and Base Fluids. The agenda today will be comprised of an introduction, followed by hydrolytic stability background, the importance of hydrolytic stability, and presenting some of the long-term hydrolytic stability assessment tested data of commercial base oils we evaluated in our study, followed by cause, mechanism, prevention of hydrolysis, and also describe what an Estolide is and how they are special and superior class of esters, and lastly, a conclusion. Hydrolytic stability. For most lubricants, oils in general, water is a very destructive element. They generally are hygroscopic, meaning that they will naturally absorb moisture from the air. So hydrolytic stability is the ability of an oil to resist hydrolysis while in the presence of water. This hydrolytic reaction, when this occurs, it forms acidic components. And in order to determine how susceptible oils are to water, we have to perform analytical tests to determine when or how much hydrolysis will occur with the specific base oil. I also want to mention, additives can either hurt or help hydrolytic stability. Some additives have high TAN. And these typically can cause rapid hydrolysis as well, leading to faster breakdown. The additives also can be added to actually catch acid catchers, to function as acid catchers, such as epoxides or carbodiamides. They're kind of like water scavengers as well. But it's important to consider these other type of additives because they can also impact other properties such as oxidation, ecotoxicity. Hydrolytic stability, why is it important? Well, 80 to 90% of hydraulic failures are due to air and water contamination. And how this contamination occurs is moisture enters the equipment eventually there's a chemical reaction that happens at the metal surface. This chemical reaction is called corrosion. And this happens over time when they come in contact with other elements. Here's a picture on the bottom of the screen showing two steel bearings. One's freshly clean, one's been exposed to water and air. And you can see that's rusty, it's been corroded. So it's really important for a lubricant to resist hydrolysis. And if it can do that, it can greatly affect the machinery's lifespan and ultimately the performance. What are the effects of hydrolysis on oils? Well, when hydrolysis occurs, you actually can get into some of these items that are listed on this slide here. Rust, corrosion, formation of acid solids. Solids are a negative effect, especially when you're trying to pump. When the instrument has a pump, degradation of the oil can lead into viscometric changes impacting BI, equipment performance, affecting seal swelling. This can lead into leaks, spills, poor machine performance, leading to decreased load carrying capacity of an oil. And with all these negative effects, eventually these parts are going to have to be replaced. And when parts are replaced, there's monetary losses dealing with the spills or purchasing new parts or even the labor to do all this work. And lastly, there's a loss of productivity because the machine is down and it's not being very beneficial and making any profit when it's not in operation. Hydrolytic stability, I just want to describe this one slide. There's essentially 5 groups of base oils, group 1 to group 5. Conventional is group 1, solvent refined. Hydrotreated is group 2. Group 3 is essentially a hydrotreated, rigorously hydrotreated base oil. Group 4 is synthetic, dealing with polyalpha olefins, PAOs. Group 5s are synthetics, and I mentioned through group 1 through 4, but these are comprised of esters, PIOs, PAGs, and estolides. So I just want to describe some synthetic esters and applications. So esters can be categorized in 2 categories. One of them is which naturally produce triglycerides either from plants or animal sources. And the other class is synthetic esters derived from carboxylic acids and an alcohol in a manufacturing setting. So these carboxylic acids are usually derived from triglycerides to get your monomeric fatty acids. Triglycerides, they have found many uses in hydraulic oils and also as base and grease formulations. But there's some downsides to using triglycerides in their form. Mainly, there's some poor temperature stability, especially when water is present. They do hydrolytically cleave, leading to machine damage and seals due to the acidic components that are formed through the hydrolysis reaction. Synthetic esters is after triglycerides, which were really one of the first class of esters to be evaluated in the lubricant world. Synthetic esters followed after that, so they really wanted to look at some other classes here. So traditional monoesters, dibasic esters, complex, polyaromatic, and estolides. And so, with these in mind, they found many uses and a whole wide range of applications. They were used to address polarity, solvency to dissolve additives, whereas some of those group nonpolar base oils they tend to have a difficult time dissolving some of those polar additives, especially. They exhibit very high viscosities, lubricity, corrosion protection, and oxidative stability. But there's always an area with esters. Lubricant formulators tend to have high criticism, especially when dealing with hydrolytic stability. So the hydrolytic stability of esters, when it relates to hydrolytic stability, most group 5 esters typically perform very poor with this test. That's because these esters are very susceptible to nucleophilic additions to the carbonyl position. So when water attacks the carbonyl, it splits into 2 parts, carboxylic acid, acidic component, and an alcohol. When this fatty acid or carboxylic acid species is formed, that acts as a source of acid catalyst, and it participates in further hydrolysis. And in fact, it actually accelerates hydrolysis. And the rate at which this hydrolysis occurs, it depends on the temperature. So the higher the temperature, the rate of formation of hydrolyzed products is higher, and vice versa. But we have to remember that this hydrolysis reaction is reversible. There's an equilibrium that lies between this reaction. So hydrolysis can be in the potential forward and reverse reaction, but in most cases, this reverse reaction is very slow. So here's a mechanistic diagram of the hydrolytic cleavage of esters. Here I'm showing just a conventional fatty ester, a methyl ester of a fatty acid undergoing acid catalysis. So the first step is it protonates, generating this protonated carbonyl. Then water can undergo nucleophilic attack, generating a tetrahedral intermediate, and water then pulls this proton to regenerate the acid here, and the methoxide group leaves and generates methanol. So you got your alcohol and an acidic component, which is our fatty acid. And as this reaction occurs more readily, because we have more acid here now, eventually you're going to actually be generating a higher population of fatty acid, which leads to an increasing TAN, total acid number. So hydrolytic stability testing, so how do we measure hydrolytic stability testing? We use ASTM D2619. This is also known as the beverage bottle method. It assesses the hydrolytic stability of oils. Here's a picture over here in the corner that shows the hydrolytic stability test being heated. But what it does, it evaluates weight change of copper, appearance of copper, change in tan of the oil layer and water layer. And this test requires 25 weight percent of water, deionized water, 75 weight percent of oil, a copper strip, and a Coke bottle. It's rotated for 2 days, 48 hours, 93 degrees Celsius, and then the layers are separated. So this test uses a pretty large amount of water. That's just to ensure that the base oil is always exposed to full moisture saturation. So what we did was we took a look at various base oils, ranging from conventional esters, C18 pentaerythritol, complex esters like TMP, some PAOs, group 3, two PAGs at different viscosities. So, and also we looked at estolides as well, and we evaluated these base oils using ASTM 2619 for 48 hours. And if you look at the C18 pentaerythritol and complex esters, there was a remarkably increase in acid number for pentaerythritol, and really we were not able to get a TAN number for the complex ester because it formed a stable emulsion, which indicates that there was a high percentage of fatty acids generated in that sample because of the emulsion. It essentially made salad dressing. The PAGs and PAOs, those performed as expected. These type of base oils are known to be hydrolytically stable since they really don't have any functionality to allow water to attack. But if you look at the estolides here, these were remarkably low TAN values, and they perform like PAGs and group 3 or PAOs. So these are behaving just like these base oils here, which are known to be hydrolytically stable. We took this research a step further, and still looking at D2619. We took an Estolide and compared it to PAOs and bright stock, some other petroleum-based base oils. And we modified the test. Instead of 2 days, we ran it for 144 hours, which is 6 days. What we saw was, a very small change in acid number. It was very comparable to some of the PAOs and the bright stocks. So this just really indicates that estolides are, in fact, a class of esters that are hydrolytically stable. So we actually performed another in-house test called the hydrolytic torture test. We took the same commercial base fluids and evaluated with 1% deionized water. The amount of water used was based on worst case scenarios of lubricant contamination. And this test was performed at 180 degrees Fahrenheit for 3 months, 12 weeks, continually stirred in a sealed container. And only the TAN of the oil layer was evaluated for simplicity purposes. So the purpose of this testing was to understand the long-term hydrolytic stability of commercial base oils on the market, but also to understand how does TAN change over time when exposed to water and heat. And really, how do we differentiate estolides from conventional esters? And lastly, how do we understand how estolides compare to other known hydrolytically stable base oils, given the time period for this evaluation? So here's the testing data. We analyzed over 12 weeks. This is weeks. These are the base oils that we evaluated. So to simplify this graph here, Here's the viscometrics of the base oil evaluated. Here's to simplify the data. We put it in the graph here. These components here are showing a very high rise in tan. We evaluated tan over week, tan versus week, tan versus time. And what we saw was the conventional esters here are all in this region here. So you can see a rise in tan pretty rapidly. Where if you look at all the PAOs and the PAGs in the group 3, they remained at the baseline as expected because they're essentially chemically inert and for hydrolysis reaction. And the Estolides were essentially right above it. So here's a blow up of it actually. So this line, the blue, green, and the gray is showing that these are the Estolides, and even after 12 weeks, they're remarkably much lower than conventional type esters, and they're in the same ballpark regime as the PAOs and PAGs. So they're pretty close to the baseline. This is some more evidence that Estolides are behaving and performing like petroleum-based fluids. So hydrolytic stability. What is an Estolide? Here's just this simplistic diagram of an Estolide. An Estolide is a secondary type of ester. Here's the Estolide bond. The Estolide has a lot of sterics involved with it, some stacking. So you can envision that a lot of this carbonyl is protected, and I'll show you some slides on that as well. I'd like to get into some mechanism of action and prevention to resist hydrolysis. So interestingly, last year, Trevor Gauntlet had written an article called Enhancing Esters. And he showed that some model studies show significant effect on hydrolytic stability, and it was a steric hindrance effect. This is the bulkiness, how bulky something is. And so he evaluated these two molecules there. He reported that these two molecules underwent a hydrolytically stability test for 120 degrees Celsius for 2 days. And what he found was, when you have this ester group here, which is 2-ethylhexyl versus C16 group, what he found was that this molecule performed 2 times, it was 2 times more hydrolytically stable compared to this molecule here. And it's due to sterics. This alpha group is providing more bulkiness, more steric hindrance, protecting this carbonyl from being attacked. So it lasts they resist hydrolysis two times more than this molecule. Very interesting. With this slide, Estolides, they provide exceptional protection against hydrolysis. But why are they more resistant to hydrolysis? So I did some, molecular modeling computations, and so you can see a picture down here showing a generic structure of an Estolide. As I said before, Estolides are secondary esters, and secondary esters are more stable than primary esters. There's some steric hindrance, molecular complexity. As the bulkiness of a substituent increases, so does the steric effect as well. When you increase steric effects, the hydrolysis rate also decreases. So steric effects, in a sense, they obstruct the reaction site accessibility. And with that in mind, it actually generates more strain in achieving the transition state. So molecular rotation movement around an sp3 bond is well known, and there's a lot of sp3 molecular rotations in these type of molecules, which helps protect the carbonyl moiety, and also an enhanced blocking of the carbonyl. With Estolides being a secondary ester, it actually increases branching. So that's another form of Sterics, and also molecular complexity. So based on this information, water has a hard time attacking the carbonyl because the molecular structure of Estolides. And there's many molecular conformations. You know, in this picture here, it's just a static picture, right? This is just, it's fixed. But when it's in solution, when it's in liquid form and being heated, there's a lot of molecular interactions that occurs. So this slide is Sterics, ester stability, and spatial influences. As I said before, secondary ester stability has been shown, it's been studied back in the 1930s and 40s, and this paper here shown on the slide, they evaluated the stability of secondary versus primary, and they showed that secondary was much more stable. And they also described some spatial influences as well in polar group clusters. So here on the right here, I'm showing triglyceride and a TMP ester. What I wanted to show here is, I think the amount of polarity in a group, I'm calling polar group clusters, can impact how water is being accessed to carbonyls. So if there's large clusters of electronegative atoms in the group, you're going to have a higher chance of water being aggregated there. So, and then that leads to, you know, poor hydrolytic stability. And so with Estolides, the spatial influences is that we need to have separation of polar groups, and Estolides does that. All the polar heads are separated, much more than some of these triglycerides or TMP esters that are shown here. So here's another 3D image in static view. You can see that there's this carbonyl has been blocked. Here's another group that's blocking the carbonyl. But here's a better, we used ChemDraw to calculate the minimized structure energy for this Estolide here. But we took it a step further and we did 3D modeling of this simple Estolide here, and we evaluated the molecular mechanics of about 1,700 unique conformers. And interestingly, we found that the top part, here's the Estolide. On this side here, we saw a hydrophobic collapse. So this chain is blocking the accessibility of water attacking. This clearly explains the Sterics involved in helping protect the carbonyl from hydrolysis. And then we have a spatial view of the Estolide shown in the space filling perspective, blocking the carbonyl as well. So some of the items to really heavily consider to prevent hydrolytic cleavage based on this data that we presented, to really slow down the hydrolysis of a base oil, especially esters, we need to start with a very low total acid number, since acidic components tend to catalyze that hydrolysis reaction. The base oil also needs to have a high degree of molecular complexity, and also provide exceptional steric hindrance features as well. They have to be oxidatively stable and great demulsibility characteristics. So if you don't have great demulsibility, you tend to form emulsions. That means you have more water in the base oil. So therefore, there's a large chance that that base oil is going to go into hydrolytically cleave, especially in the, when heat is being applied. So conclusions. So based on this presentation, esters are definitely used in petroleum replacements, but there's a lot of negative criticism on esters, especially in aquatic applications. They tend to thermally hydrolyze in the presence of water to organic acids, and this ultimately leads to high total acid number and eventually affecting the metalwork and equipment in a negative manner. So Estolides are another class of esters, a very distinct class of esters, and they, from this research that I've presented today, I hope I've shown that they have demonstrated very high hydrolytic stability compared to other traditional esters, and that they really perform very close, and they behave like PAOs in terms of hydrolytic stability. So, this actually opens up another realm for formulators to use Estolides or esters in their formulations. And so the next step, we actually plan on evaluating the same study, extended study, but in the presence of specific metals and other metal alloys that require lubricants for operation. I'd like to thank you for your time. I hope you enjoyed the research that we presented here today. I'd be happy to address any questions that you may have. And I'd like to thank STLE for the opportunity to present this research. Thank you very much. Have a good day.